Welcome back, guys. Today we want to conquer half and full adders. So let's dive straight in. Despite their complexity, CPUs are built from millions of tiny switches. At their very core, they only understand very basic operations like comparing numbers, moving data, and crucially adding two bits together. If we recap the basics of binary addition that we have learned in the video I've linked in the description below, you'll remember that in binary, we can't deal with numbers more than one digit. So I always do my maths like this. So we know that 1 plus 0 equals 1. 0 plus 1 equals 1. However, 1 and 1 equals a 0. And because we can't put two digits next to each other, we carry the 1 to the next column. And the way I do it is 1 plus 0 equals 1. And when we combine these two digits, these two bits, that makes 2. To create the process of addition, we can use the following logic circuit. Here we can see that we have an XOR gate and an AND gate, and they take two inputs. So they both take the same two inputs, and our output S for sum, and our output of the AND gate is C, which we call carry. We can see the truth table here demonstrates that S for sum uses the XOR gate to add 1 to the output only if the two variables are 1. So you can see that here. C, the carry, uses the AND gate to only output 1 if both variables are 1. For multi-digit addition, we need a full adder. It adds 3 bits, A, B, and the carry-in from the previous position. And as you can see here, this setup can be daisy-chained to add more adders in order to add more digits together in a binary sequence. Now, because we have 3 inputs, if any of the two inputs is a 1, then the result of the sum is a 0, because the input still needs to be exclusive 1. So you can see here, if any of the 3 inputs are a 1, then the sum, which you can now see in the highlighted blue column, still has to be exclusively 1 in order for the output to be a 1. The exception to this, as you can see in the last row here at the bottom, is when all 3 inputs are a 1. This is because of the use of the OR gate for the C out. This also makes perfect sense because we know that 1 plus 1 plus 1 is a 3, and we know that in binary, 3 is represented as 1, 1. And you can see that here in our binary addition example. Okay guys, so this one's quite a short video. As always, please click on the link on the video and there's some exam questions for you guys to try out and practice the skills that we've learned. And I hope to see you in the next video.